continue our unit 2 with the design of a staircase. And as we did for the floor slab, we set ourselves another question. And our question reads: design and detail the staircase using the limit state method outlined in the BS 8110 part 1. Now this will be the procedure for our design. We'll begin by doing our initial or preliminary sizing. We'll estimate for the loads on the staircase. We'll analyze our staircase for moment and shear. We'll check whether the initial dimensions we came out with for our staircase is adequate to resist the moment and shear. Then we'll design for our moment reinforcement, design for shear, do our deflection check, and end everything with our crack check. Now for our design data, we are making use of the same data that we used in our slab design, in which case we had our exposure condition being mild, our minimum grade of concrete being C30, the nominal cover to reinforcement for durability being 25, and that for fire safety being 25 as well, with our minimum dimension for fire resistance being 20. For our grade of reinforcement, as we did for the slab, we are making use of the mild steel with a yield strength of 25 newtons per millimeter squared and a diameter of 12 millimeters. So then we move ahead and locate our staircase within our floor plan, and our staircase has been highlighted for us in the red. So then we are designing the staircase within the red highlighted region. This is a plan view of the staircase to the right and a section through the staircase. Our staircase is connecting the first floor slab to our ground floor slab and is made up of 2 flights of staircases, one from the first floor to the middle landing and the second one from the middle landing to the ground floor slab. Now generally in designing a staircase, we design for each flight separately. So for our example, we are going to pick the flight between the first floor and our landing, and that's what we are going to use for our design. Now we move on to look at our initial dimensioning. For our initial dimension, we'll start by picking out our effective span for the staircase. The BS code states that the effective span for the staircase is given by the formula as stated on the board, where the LA is the length of our stair flight, the LB is the length of the support, be it a column. We'll begin our design by first coming out with the effective span of our staircase. Now the effective span of our staircase given by the BS code is equal to our flight length plus half of our support dimensions. Now the support dimensions can come in the form of beams, in which case we have the slide. We'll start our design by first establishing our effective span for the staircase. The BS code states the effective span for a staircase as being equal to LA plus half LB1 plus LB2, where the LA is the length of our stair flight or the planned length of the stair flight, and LB is the dimensions for the support at both ends of the stair flight. Now at both ends of the stair flight, the support can be in the form of a beam or a landing. Where the stair flights terminate exactly at a beam point, then the beam becomes the support for the staircase. But then at the end of the flight, if there is a landing before a beam comes, then the landing becomes the support for our staircase. And in the case of the staircase we are designing for, we have a support at the top part of the beam with a dimension of 725 millimeters. Then at midway through our stair flight or midway through our staircase, we have another landing with a dimension of 1325, and for our flights it has a dimension of 2700. So then for our effective span, it becomes 2700 plus half of the 725 plus the 1325, giving us 2700 plus half of 2050. This gives us 2700 plus 1025, and ultimately gives us our effective span of the staircase as 3725 millimeters. Now, having established our effective span, we now move ahead to establish our initial dimensioning. And primarily by establishing our initial dimensioning, we want to see the thickness that we can give to the waist of our staircase. So then, just as we did for our floor slab, we now move to our staircase and we apply our span to depth limits. Now, because our staircase is simply supported is simply supported by our landings, our span to depth limit is going to be 20, as we saw when we went through the span to depth limits during our slab design. Now, according to the BS code, if you have a staircase in which the flight or the span of the flight is equal to or more than 60% of the effective length of the staircase, the span to depth limit is supposed to be increased by 15%. If we take the staircase that we are designing for, our flight is 2,700 and our effective span has a value of 3,725. We can realize that, or would realize that the distance or the length of our flight is more than 60% of what our effective span, in which case our limited value, which is 25, has to be increased by what? 15%. That is how come we have our limiting value being multiplied by the 1.15. Now, this gives us a limiting value of 23, and by inequality, our effective depth now becomes the span of the staircase divided by the 23, which is our limiting value. Now, this gives us our D effective of 3,725 divided by 23, which ultimately yields 161.95. Now, having found the effective depth, we now move ahead to establish the total depth of our waist. Now, the total depth of our waist will be equal to our effective depth plus our concrete cover and half of our bar diameter. We just calculated our concrete cover as being 161.95. From our design data, our cover to reinforcement is 25, and because we are making use of 12 mild steel bar, half of our bar diameter is going to be 6. This gives us a total depth of 192.95 millimeters and can be approximated to 200 millimeters. But then, just as we realized under the floor slab design, if I have a slab which is very, very thin, then the slab would feel in movement before it feels in shear. So under such a principle, I can design my slab only for movement without shear, since before the load increases to a point where it would feel in shear, it would already have failed in what? In flexure. So then, instead of making use of the 192.95 depth, we are going to reduce our waist depth to 150 in which case we design our staircase only for movement and not for shear. So then an overall depth of 150 is assumed, in which case our effective depth would also change. Now, once our effective depth changes, we'll have to come and estimate for a corresponding effective depth for an overall depth of 150 millimeters. So then our new effective depth becomes the overall depth minus our concrete cover plus half of our steel reinforcement. Going forward, this gives us 150 minus 25 plus 6, where the 150 is our new assumed depth, the 25 is our cover to reinforcement, and the 6 is half of our bar diameter. This gives us a D effective of 119 millimeters. So then, for an overall depth of 150 our D effective for our staircase is equal to 119 millimeters. Now, having established our initial depth, we are now going to move forward to look at the loads that our staircase is supposed to support. Now, with that, we move on to do our load estimation. And under our load estimation, just as we did for the slab, we are going to estimate for our dead loads and our live loads. So we'll begin with our dead loads. Now, under the staircase design, the following would fall in, or the following will be considered as part of our dead load. We have the waist of the staircase, the individual steps that makes up the staircase. We have the landing of the staircase, considering both the landing at the top and the landing at the bottom, and the finishings that would be given to our staircase. Now, just as we did for the floor slab, we go back and we visit the BS648, particularly focusing our attention at the section that gives us the densities for our concrete material. Because we are going to make use of granite as our aggregate for the concrete, And granite being a natural aggregate, we'll go and pick the density for concrete, which is prepared making use of the natural aggregate. And so with that one, our density becomes 2,307 kilograms per millimeter squared. So we pick this value and we are going to use that value to estimate for the self-weight of the various items that has been listed. Now, as an example, we'll start by estimating for the self-weight of the waste. And as we did again for the slab, we realize that in calculating for the self-weight of the waste, since self-weight or weight in itself is a force, we can calculate for that making use of our density, our volume, and our acceleration due to gravity. Once we multiply our density to the volume to the acceleration due to gravity, it will yield us the weight of whatever element we are calculating for. So then we have a density value of 2,307. For the volume of our waste, it's equals to 1 meter, since we are designing for, or since our step flight has a 1 meter width, the volume is going to be equals to 1 meter multiplied by 3.087 multiplied by 0.15 multiplied by 9.8, where the 2.07 is our density, our 9.8 is our acceleration due to gravity. Now for the value of 3.089, how did we arrive at that value? If we take the stair flight that we are designing for, our flight has a planned length of 2,700 and a height of 1,150. Sorry, and 1,500. So this is 1,500. This here is 2,700. Now, considering the waist of our staircase, the waist is an inclined element. So then in calculating for the volume, we would have to make use of the inclined length instead of the planned length. Hence, we can't use the 2007, which is the length of the flight, to calculate for the volume of our waist. So then we would have to come and find the value for the inclined length of the waist, which is being marked as x. Now, making use of our Pythagoras theorem, we know that x would be equal to the square root of 2.7 squared plus 1.5 squared. Now, solving everything through gives us a waist length of 3.0886 meters, which translates to 308.6 millimeters. Hence, for the volume of our waist being equal to the 1 meter multiplied by 3.089 multiplied by 1.5. Now, multiplying these values through would give us a total weight of our waist as being equals to 10.457 kilonewtons. So then we can append that value against our waist. Now, the same process can be followed in to determine the value of our step, whereby we pick the individual step, multiply it by the volume of the step. We pick in the same method can be applied to determine the weight of the various elements left, i.e. the step, the landing, and the finishing. For the step, we'll pick the individual step, calculate for the volume, multiply the volume by the density and the acceleration due to gravity, and multiply it again by the number of steps that we have on the particular flight. That will then give us the total weight of the steps that the stair flight is supposed to resist. So then, having done that one, we realize that the weight of our step for the flight that we are designing for has a value of 5.086 kilonewtons. Applying the same method to the landing and the finishing will yield us a landing weight of 6.952 kilonewton and a finishing with a weight of 0.756 kilonewtons. Now, summing all of these values together gives us the total dead load for our floor, for our staircase, which is of a value of 23.269 kilonewtons. Now, having finished establishing the dead load for our staircase, we'll now move ahead and determine the live loads on our staircase as well. Now, in determining the live loads of our staircase, the BS code permits that whatever load has been used in designing the floor slab can be superimposed on the staircase, in the absence of which. Now, in determining our imposed loads, the BS code permits that whatever live loads was used in determining was used in the design of the floor slab can also be superimposed on the staircase for its analysis, in the absence of which a rigorous method would have to be undertaken to determine the exact live loads that the staircase would have to resist. Now, because for our staircase we made use of a live load of, because for our slab we made use of a live load of 1.5 kilonewtons per millimeter squared, in designing for our staircase we are going to superimpose the same live load as we used for our slab on our staircase. So then for our staircase, our live load or our imposed load is going to be equals to the uniform load as we impose on our floor slab multiplied by the planned area of the staircase. Unlike the waste where we looked at, or where we calculated for the inclined volume of the waste, when it comes to the imposed load, in determining the weight or in determining the load that the staircase is supposed to carry, we make use of the planned area and not the inclined area of the staircase. So then for our imposed load, our uniform load value is 1.5 kilonewtons per millimeter squared, and our planned area is equal to our effective length or our effective span multiplied by the width of the staircase, which is 1 meter. So then we have it being equals to 1.5 multiplied by 3.725, which is again multiplied by 1, and this gives us a value of 5.587 kilonewtons. So then for our live load on our staircase, it has a value of 5.587 kilonewtons. Now, having established our dead loads and our imposed loads, we can now move ahead and determine our design load for the staircase, in which case our design load is equals to 1.4 multiplied by our dead load plus 1.6 multiplied by our live loads. This gives us 1.4 multiplied by 23.269 plus 1.6 multiplied by 5.59, in which case we've approximated the 5.587 to 2 decimal places. This gives us a value of 32.58 plus 8.94, with an ultimate design load value of 41.52 kilonewtons. Now, having been able to determine our ultimate design load, we now move ahead and determine the amount of movement that our section would have to resist. According to the BS code, the amount of movement that our staircase would have to resist at the midspan and at the support point is given by the formula M equals WL over 10, where W is the imposed load on the staircase, L is the effective span, and M is the applied moment. So substituting the values into it, our imposed load was 41.52 kilonewtons multiplied by our effective length, which is 3.725, divided by 10. This gives us a moment of 15.578 at our support point, or at the point where we have our landings, and at the midspan of our staircase. Now, once we've determined the moment within our section, we'll now want to go and revisit the initial dimensions we gave to our staircase to be sure that these initial dimensions would be able to resist whatever moment that the staircase has to support. So then we go back and check whether our section is adequate. Now, for our section being adequate, because we are designing for a staircase and our staircase has a rectangular section, we are going to make use of the same provisions that we made use of doing the design of the floor slab, in which case we had our K value being equals to M over FCU BD squared, where M would be our applied moment, the FCU becomes our grade of concrete, the B becomes the width of the staircase, and the D is the effective depth of our waste. This gives us a K. Having substituted the values into it, we have our K value being equals to 15.578 multiplied by 10 to the power 6, in which case we are converting our moment from kilonewton meter to newton millimeter, divided by our concrete grade, which is 30, the width of the staircase, which is 1 meter, and the effective depth, which is 119 meters raised to the power 2. This yields us a K value of 0.036. Now the BS stipulates that for the according to the BS code, at the maximum capacity of any rectangular section, the K value is supposed to be equal to 0.156. So then we are going to compare the K value for the applied moment to the K value for the maximum section of a rectangular beam, or for a rectangular section, in which case our K value there would be 1.56. And the BS code states that at the maximum moment of a rectangular section, or at the maximum moment capacity of a rectangular section, the K value at that moment is equals to 0.156. And the BS code has assigned a K prime to that 0.156. So that in deciding whether our section is adequate or not, we found the K value corresponding to the moment that we've calculated for, and we are supposed to compare that K value to the K value of our maximum moment capacity that our section can take, and that one is equals to what? 0.156. Now comparing the two values, we realize that the K value for our applied moment, which is 0.036, is lower than the K value for our moment capacity, which is 0.156. Now once we have our K value for the moment applied being lesser than the K value for our moment capacity, it means that we can move ahead and design our section as a singly reinforced concrete section. So then for our staircase, we are going to design it as what? As a singly reinforced concrete section. Now having arrived at that conclusion, we'll now move ahead and design for the moment, or we'll now move ahead and design our moment reinforcement. And again, with reference to the procedures we went through whilst designing for the slab, the area of our moment reinforcement is equal to our moment value divided by 0.95 multiplied by our steel grade and our lever arm. But then the BS code once again limits us to the value of the lever arm that we can use, and the value of our lever arm is not supposed to exceed 0.95 of our effective depth. In that regard, we substitute the value of our lever arm for the 0.95 of our effective depth. Now this yields us with an area of steel of our moment divided by 0.95 of our grade of reinforcement multiplied by 0.95 of our effective depth. Substituting our values into it, we have our area of steel required being equals to 15.578 multiplied by 10 to the power 6, everything divided by 0.95 times 250, which is the grade of our reinforcement, multiplied by 0.95 times 119, which is our effective depth. This gives us a total area required of 580.20 millimeters squared. When we substitute our values into it, we'll realize that our area of steel becomes, or is equal to 15.578 times 10 to the power 6 divided by 0.95 multiplied by 250, which is our grade of reinforcement, again multiplied by 0.95 multiplied by 119, which is our effective depth. Now this gives us a total area of reinforcement required of 580.20 millimeters squared. Now, because we are making use of mild steel, we are making use of 12 mm mild steel reinforcement bar, we'll move ahead and calculate for the area of one 12 mm bar. Whatever area we get, we'll come and pick the 580.20 and divide it by that area to give us the number of reinforcements that would have in our section. So then, because we are supposed to provide an area of 580.20, we'll pick the 580.20 and divide it by the area of one 12 mm reinforcement bar. Now once we divide it by that area, whatever value we get, we round it up to the next whole number. Whatever value we get, if it's in the decimal form, then we round it off to the next whole number, and that would give us the number of reinforcements that would require per meter span in our staircase. Now, having gotten that number, we divide the 1 meter span by the number of reinforcements we have in our section. That would give us the spacing to which we are supposed to what? Provide for our reinforcement. Having gone through that exercise, we realize that we have to provide for our 12 number reinforcement bars. We'd have to provide them at 175 centers, and the total area for the number of bars that would be required would be equals to what? 646 millimeters squared. So then, even though our section is requiring an area of 580.20, we are providing 12 millimeter diameter bars at 175 millimeter centers, and the area for the total number of reinforcement that would give us the 175 millimeter center to center is equals to what? 646 millimeters squared. So then this is the amount of reinforcement that would be put in within our staircase. Now, having determined on our moment reinforcement, we'll move on and look at our design for deflection. As stated earlier on, because our section is very, very thin, or our section is not that thick, we can make do without designing for shear reinforcement, because it's been stipulated that if you have a floor depth which is less than 200 millimeters, the floor depth will first fill in flexure before it fills in shear. So now once we have our floor depth, or we have our waist depth being less than 200 millimeters, it means that our waist would first have to fill in flexure before filling in shear, in which case we will just have to design for our section in flexure and can neglect or can go by not designing for our section in what? In shear. So then we are not going to design our staircase for shear. With that being said, we'll move on and look at our design for deflection. Again, we'll revisit our span to depth ratios that we made use of whilst doing our stairs, whilst doing our slab design. And we said for our actual deflection, it's equal to the effective span divided by our effective depth. As we realized earlier on, our effective span for our staircase, or for our stair flight that we are designing for, was 3725, and our effective depth being equals to 119. Dividing the 3725 by 119 gives us a value of 31.30. Now we are supposed to go and compare this 31.30 to our allowable deflection, or to our deflection limits given in the BS code. And for our deflection limit, as we realized earlier on, again doing our initial dimensioning, our deflection limit was 23, and that 23 deflection limit was for a concrete section without reinforcement. So once we've been able to introduce reinforcement into our concrete section, it means that we'll have to move ahead and modify our deflection limit, in which case our allowable deflection now becomes our 23 limit multiplied by our modification factor. Just as we did for the floor slab, our modification factor comes with the formula 0.55 plus 477 minus fx, all divided by 120 into bracket 0.9 plus m over b d cube. Our fs, again as we saw from our slab design, is given by 2 multiplied by our grade of reinforcement, again multiplied by the area of reinforcement required, and all of that divided by 3 multiplied by the area of reinforcement approved. From the foregone calculations, we realize that our area of reinforcement required was 580.20, with our grade of reinforcement being 250. So then for our fs value, it's going to be equals to 2 multiplied by 250 multiplied by 580.20, and everything divided by 3 multiplied by 646, which is the area of reinforcement we provided within our stair flight. This gives us an fs value of 149.62 newtons per millimeter squared. Now, having established our fs value, we'll now move ahead and establish the value for our m over bd cube. Our moment value, as we calculated, was equals to 15.578 multiplied by 10 to the power 6. That is quoting our moment value in terms of what? Newtons per millimeter squared. Our b value as our m over bd squared is given by 15.578 times 10 to the power 6. That is taking our moment value in terms of what? Newton millimeter. And our bd squared being equals to 1000 multiplied by 119 squared. Now, the product of all of these is equals to what? 1.10. Now, having established our fs value and our m over bd squared value, we can now substitute these values into our modification factor equation, which is at 0.55 plus 477 minus 146.62, all divided by 120 into bracket 0.9 plus 1.10. This gives us a value of 0.55 plus 1.36 and a final modification value of 1.91. Now, per the premise of the BS code, our modification value should not exceed 2.0. So then comparing this to the limit set out by the BS code, we realize that our modification value that we've calculated for is lesser than the upper limit given by the BS code, in which case we are supposed to make use of our modification value. So therefore, we'll move ahead and use a modification factor of what? 1.91. Now, applying a modification factor of 1.91 to our allowable deflection gives us a new allowable deflection of 43.93. Now, we'd have to go and compare these 43.93 to the actual deflection that we calculated for, to see whether our deflection falls within the limit or we've exceeded our deflection limit. Now, comparing it to the actual deflection, for our actual deflection, we had a value of 31.30, and for our allowable deflection, having a value of 43.93. Comparing the two, you realize that our actual deflection is below or falls below our allowable deflection, in which case our deflection falls within the limit set by the BS code. And so we can go ahead and say that our deflection check is what? Okay. Meaning that our stair flight wouldn't deflect excessively. Having finished with our deflection check, we'll move ahead and look at the crack check for our stair flight. And again, we'll make use of the same provisions that we made use of whilst designing for our slab. Now, while designing for our slab, we made use of the section 3.12.11.2.7 of the BS 8110. And the section states that in no case should the clear spacing between bars exceed the lesser of 3 times the effective depth, or 750 mm, whichever is the lesser. Now, aside the first provision, it moves on to say that in addition, unless crack widths are checked by direct calculation, the following rules would ensure an adequate control of crack for slabs subject to normal internal and external environment. The first condition says that no further check is required on bar spacing if either grade 250 steel is used and the slab depth does not exceed 250 mm. Grade 250 steel is used and the slab depth does not exceed 250 mm. If we look at the reinforcement that we made use of in our slab design, we made use of the mild steel bars with what? A grade of 250 newtons per millimeter squared. And our waist depth was 150 mm. So then for our slab design, our thickness of slab was equals to 150 mm, which is lesser than the 250 being stipulated. And we also made use of the mild steel bars. And because we have our slab depth being lesser than the stipulated depth, it means that we don't need to do any other check per the recommendation that we've just read. We don't need to go ahead and do any other check on our staircase for crack. But then we'll go ahead and apply the first principle that we looked at, which states that in no case should the clear spacing between the bars exceed the lesser of 3 times the effective depth, or 75 mm. So then we go ahead and calculate for our clear span or our clear spacing. The clear spacing between our reinforcement bar would be our center to center spacing less the bar diameter. And for our span or for our stair flight, we had our center to center spacing being equals to 175 and our bar diameter being 12 mm, in which case our clear spacing is equals to 163 millimeters. Now, determine our 3 multiplied by d effective. Our depth or effective depth had a value of 119. Multiplying it by 3 gives us a value of 357 millimeters. Now, comparing our clear span to our 3 multiplied by effective depth, we realize that our clear span is below the value for our effective depth multiplied by 3, in which case our crack check can also be said to be okay. Or we can move ahead and say that per the spacing we've given to our stair flight, our stair flight will not experience excessive cracks, or the cracks within our stair flight would be within a minimum limit. So then, having gone through our crack check, we have done with design. And the next thing for us is to convert whatever we've calculated for in the design into appropriate drawings. And an example of the drawings that would have to be sent to site for the construction is what has been shown on the screen for you. So then once you're able to convert whatever calculations we've done or we've undergone into an appropriate graphical representation, then we can call our design to an end, in which case we'd say we've come to the end of our stair design. And this ultimately brings us to the end of our unit 2. Thank you very much.